Okay, good morning. Or again, whenever. We're going to start talking about enthalpy now, which is just sort of a fancy word for heat. So we're gonna sort of walk through this, and I'll show you how Q is basically the same for the most part as delta H. And then we'll probably start using delta H a lot more often than Q. But you need to understand how those are interchangeable and how they are not. So first, let's talk a little bit more about work. We were talking about this yesterday. If you have an open container, or even a container that's allowed to expand and contract naturally when we have gases in it, then most of the time the only work done is going to be a change in volume. Okay, so now if you have a completely closed container and you heat up a gas, then you're going to have a pressure change also. Okay, but typically the kinds of experiments we do in this class, the kind of labs that we do in regular chemistry or in AP chemistry, we're going to do them in open containers, so usually the pressure is going to stay right around atmospheric pressure. Okay, so then the work that's done in a system when we do a chemical reaction is typically just going to be a change in volume. Okay, one way or the other. So either the reaction we're working with, the system will contract and the surroundings will push on it, or it will push out against the system or against the surroundings. Okay, now the way that we measure that is by the formula W equals negative P times delta V. Okay, now again, the reason that this is the only thing that has a delta with it, delta means change in, is because this is typically the only part that's actually changing. The pressure typically remains constant. So if we multiply the pressure times the change in volume, that's going to give us the work that's being done in that particular situation. Okay. So an example of this they have here, we've got a movable piston here that can move up and down based on the expansion of the gas that's inside this tube. Okay. There's a bunch of gas particles in here. When you add zinc into this container, and this is then closed off so that no gas can escape that direction, and you put that zinc into hydrochloric acid, that's going to make some hydrogen gas. That's the reaction that happens here. So the hydrogen gas plus what was originally there is going to push the piston up, okay? Because now there's more gas in there, so that's going to increase the gas pressure momentarily until it's able to move that piston up, and then it's back to normal atmospheric pressure. So the work done there is basically the change between where the piston originally was and where the piston now is, okay? And then so you take the pressure times the change in the volume. We can calculate the work that way, okay? Now, enthalpy is basically constant pressure, okay? So we're talking about heat flow that happens at a constant pressure, then we're talking about enthalpy. And so that's a little bit different than heat, in the sense that when we talk about heat, we could be talking about any, heat flow anytime, even if the pressure does change or that sort of thing. But if we're dealing with a constant pressure situation, okay, which again is like this example back here, because the piston's able to move, so that keeps the pressure the same. Any open container that you have, any reaction that we do in a beaker is going to be a constant pressure reaction because, you've got the solution down here, and it's reacting, but it's open to the atmosphere, so there's a free exchange of gases between the two, so the pressure is going to be constant there, okay? So anytime we have a constant pressure, the heat equals the enthalpy. They're basically the same thing. Well, okay, heat doesn't exactly equal the enthalpy, but they're basically, we can use those terms interchangeably when we're talking about a constant pressure situation, okay? So enthalpy is internal energy plus the product of the pressure and the volume, okay? So it's the internal energy essentially plus the work that happens there, okay? And that's how we define H. Now, here's how we're going to derive the fact that H is basically the same thing as Q. Or delta H, I guess, is basically the same thing as Q. So when we have the system changing to constant pressure, then we just put a delta in front of both of these, okay? Delta H equals delta everything on this side, okay? And that can also be written if we distribute this. Now again, this is at constant pressure, so the P doesn't need a delta because it's not changing, okay? Delta E plus P times delta V, okay? Now we just talked about how this right here, this expression, is actually equal to the opposite of work, right? Because work equals negative P times delta V, okay? So this expression right here is equal to negative W. So we need to keep that in mind, okay? And then we also know that delta E from yesterday equals Q plus W, okay? Heat plus work. So then, if we plug those into the equation, if we substitute all of this through, okay, delta H equals Q plus W, that's the delta E part, right? And then the P delta V part, that's the negative W part, okay? If we plug all that in, the W's, the work, cancels out, and delta H equals Q, okay? And so, basically, again, all of that just to show you this Q expression that we've been talking about. It represents heat change or heat flow. At a constant pressure can also be represented by delta H, okay? We're also talking about heat change here. Now this is technically, delta H is technically called enthalpy, okay? So when you see the word enthalpy, from here on out, pretty much all the problems you get on the AP exam are done at constant pressure when they're dealing with this sort of thing. Okay, so from here on out, when you see delta H, you can think enthalpy or heat. Okay, but I want you to be familiar with both of those terms for that. So that's delta H. Okay, now we're going to use delta H a lot. Whoops, sorry. Get rid of some of this stuff here. Okay. So at constant pressure, change in enthalpy is the heat gained or lost, okay? So again, enthalpy is a little bit broader definition than just the heat gained or lost, but at a constant pressure, delta H, the enthalpy and the heat gained or lost are the same thing, okay? All right. Endothermicity and exothermicity. I guess those are words. They're in the book, so I'm going to go with it. So now we're getting to something that you're a little more familiar with, endothermic and exothermic, okay? We just need to know how those relate to delta H, okay? So when delta H is positive, that means that heat is flowing into the system, okay? You can see this picture here. Heat is flowing into the system when delta H is positive. It's increasing the delta H of the system, okay? Or it's increasing the H, I guess, of the system. That's why the delta H is positive. Okay, so the heat's flowing into the system. That means it's endothermic. The heat is going in. And then, obviously, the reverse process is true, okay? It's exothermic when delta H is negative. So when heat is flowing out of the system, that means delta H is now smaller than it was before for the system. So it's going to be negative. The change is negative, okay? And that means it's exothermic. The heat is flowing out. So delta H is positive equals endothermic. Delta H is negative equals exothermic. You just need to keep that in mind, okay? All right. Didn't leave myself a lot of room for this one. Indicate the sign of the enthalpy change delta H in each of the following processes carried out. Well, but we just have to put a positive or a negative here, so that's, I don't need a lot of room. Indicate whether the process is endothermic or exothermic. All right, so letter A here, an ice cube melts. Okay, so we got to think about this for a second. In order for an ice cube to melt, we actually have to put heat into the ice cube, right? So if our ice cube is the system, then we're putting heat into it. That's an endothermic process, okay? So it's absorbing heat, and that means that the delta H is positive, okay? All right, we've got 1 gram of butane, and it's combusted and sufficient oxygen to give complete combustion to CO2 and H2O. Okay, combustion reactions, I think we probably all know this. When you have a fire, it's giving off energy. It's releasing energy out into the environment. That's why if you get your hand too close to it, your hand being part of the surroundings is going to get too much energy too fast, and you're going to get burned. Okay, and so that system is giving off a lot of energy, which means it's an exothermic process. Okay, which means that the delta H for that process is negative. And then a bowling ball is dropped from a height of 8 feet into a bucket of sand. Okay, so we talked about this the other day. When the bowling ball gets dropped, there's 2 things that are going to happen. First of all, the bowling ball is going to have some work done on it. Now, you're not going to notice that very much because the bowling ball is fairly rigid. It's not going to distort like the clay ball that we talked about the other day. But the bowling ball is going to do some work on that sand. Okay, so work is done there, but we're talking about delta H, the enthalpy change. Okay, and so we want to know what happens as far as heat is concerned. All right, so when that bowling ball hits the sand, there is some energy given off in the form of heat because there's some friction there and that sort of thing. Okay, so the system is actually releasing some energy there when that happens. Okay, so the delta H for that one is going to be also negative. That's an exothermic. Okay, the bowling ball is not going to absorb heat when it hits the ground, and neither is the sand. They're going to give off some heat. Okay, now it may not be that noticeable, but there will be some heat given off. Okay, all right, now we need to talk about enthalpies of reactions. Okay, and this is really not excuse me. Okay, this is really not that bad of a concept. It's basically, you just got to remember a couple of things that are happening here. Okay, first of all, I want you to start thinking of delta H as either a reactant or a product, depending on whether this is an exothermic or an endothermic reaction. Sorry, excuse me, it's too early in the morning. Alright, so the enthalpy change is the enthalpy of the products minus the enthalpy of the reactants. Okay, so in other words, we want to know how much enthalpy do we have to start with, how much enthalpy do we end up with, and we take what we end up with here minus what we started with, and final minus initial is going to give us the change. Okay, which is pretty typical for a reaction. Well, let me go back to this and talk about the picture here for a second. Okay, when you've got CH4 gas plus 2O2, now you might recognize here this is a combustion reaction when it forms CO2 and H2O. Okay, when you burn methane in the presence of oxygen, it gives off 890 kilojoules of heat. Okay, because it's giving it off, because it's exothermic, we write that as a negative 890. Okay, so that's our delta H for that process. Now, if we went back the opposite direction and changed the CO2 and H2O back into oxygen and CH4, the energy change for that process would be exactly the opposite. Okay, it would have to absorb 890 kilojoules of energy, endothermic process, in order to go back. Okay, so that's the way that that works. They're exactly opposite processes of one another. So if this reaction is going to give off 890 kilojoules of heat, then the reverse reaction would have to absorb 890 kilojoules of heat. Okay. This quantity, delta H, is called the enthalpy of reaction, or the heat of the reaction. Okay, it's how much heat is given off or how much heat is absorbed when a reaction occurs. Okay, and again, they're just giving another little example here. If you've got H2 plus O2 making H2O, that's going to give off some heat. Okay, so the delta H for that would be less than 0. It'd be a negative number because it's exothermic. All right. So enthalpy, so things you need to know about it. Enthalpy is an extensive property, okay? Now, it's been a while since we talked about extensive versus intensive, but that means that it depends on the amount Okay, it's not like density, where the density is always the same no matter how much you have. If you burn 1 mole of CH4, it's going to give off a certain amount of energy. If you burn 2 moles of CH4, it's going to give off twice as much energy, okay, twice as much heat. That kind of makes sense. The more methane you have to burn, the more heat's going to be generated, okay? So this is an extensive property. It does depend on the amount that you have, okay? Another thing about delta H, and we just talked about this, the delta H for a reaction in a forward direction is equal to but opposite, not equal in size but opposite in sign to the reverse reaction, okay? So again, like the CH4 plus O2 example that we talked about, it was positive, or it was negative going to CO2 and H2O, but it was positive going back the other direction. But it was the same value. It was 890 both times. And then the delta H for a reaction also depends on the state of the products and the state of the reactants, okay? So depending on whether it's a gas or a liquid or a solid, that's going to affect how much energy, how much heat is given off or absorbed by the reaction, okay? So it does depend on the state. Whoops. And I just realized, let me check something, because I think I put another example on your notes, and then I forgot to put it in my PowerPoint. And I want to make sure that we talk about that example, so give me just a second here. Okay, here we go. So let's talk about this question right here, and I'll just go ahead and write it on here. It says, how much heat is released when 4.50 grams of methane gas is burned in a constant pressure system? Okay, now again, the only reason they're saying constant pressure system is so that you know that the delta H here, we're talking about heat change, okay? And that's the only reason that they tell you that. But then they give you a chemical equation here, okay? CH4 plus 2O2. This is the equation that we were just talking about in the notes. Delta H equals 890 kilojoules, negative 890 kilojoules, okay? So this is an exothermic reaction. Now, what you can do here is you can sort of think of heat as one of the products in this reaction, okay? If it was an endothermic reaction, you could think of heat as one of the reactants because it needs heat in order to happen. But here, because it's giving off heat, you could think of it as one of the products. You could actually write this equation like this. CH4 plus 2O2 yields CO2 plus 2H2O plus negative 890 kilojoules, okay? And so you could actually sort of write it that way and think of heat as one of the products. Now, it can be written this way as well, and this is just fine, okay? But what that's telling you is for every 1 mole of CH4, if you look at the stoichiometry of this thing, for every 1 mole of CH4 that we burn, we're going to get negative 890 kilojoules. We're going to get 890 kilojoules of energy being given off, okay? So that's the idea there. Now, what they're asking is, okay, that equation tells us when we have 1 mole of CH4. That equals negative 890 kilojoules. That's how much heat is given off there, okay? But they're asking us, well, what about when we have 4.50 grams of the methane gas, okay? So we've got 4.50 grams of the CH4. And we want to figure out how much heat is given off there, okay? So the first thing we've got to do is we've got to figure out how many moles of CH4 that we have. So we've got grams of CH4, and we're going to convert that to moles of CH4. And in 1 mole, there are about 16 grams, okay? And then from there, we can go from moles of CH4 to kilojoules, okay? Because we already said in 1 mole of CH4, we end up with negative 890 kilojoules of energy. okay? And so then we just set this up like a normal dimensional analysis stoichiometry type problem. And you think about heat as one of the products or one of the reactants, depending on whether we're talking about an endothermic or an exothermic reaction. Okay, so 4.5 divided by 16 times negative 890 gives us negative 250 kilojoules. Okay, and that number should make sense because this is less than a mole, right? 4.5 grams is less than a mole of CH4 because a mole of CH4 is about 16 grams. So we should be giving off less than 890 kilojoules of energy. Okay, so that looks like a pretty reasonable number. That's how you use the stoichiometry in a chemical equation to figure out your delta H. And your delta H is usually going to be given to you just like this. Okay. All right, we're going to do a lot more practice with these in class to make sure you guys have it. That's the basic idea behind delta H and how that's used in chemical equations. All right, see you next time.